experiments, you want to stop right at endpoint so that you know that the amount of base you added matches the amount of acid exactly. If you could get it exact, then you don't have to do any kind of equilibrium calculations. It's just a stoichiometry problem. We showed that about 3 lectures ago. Today, we're going to be talking about the equilibria associated with titrations. So we're going to go through the mass action table, the ICE table, and look at what's going on during a titration, and then how to calculate all of the concentrations and pH and everything when you're not at endpoint. So you have these pH curves. After today, you'll be able to calculate a pH curve. You would never want to do that by hand, but that would be something you could put into Excel, and you could actually plot it out. Okay. So just to review, the titration's pretty complicated equilibrium problem. You have a known amount of acid that you put in. If you're titrating with a strong base, you put in a known amount of acid, put in an indicator, the base is in the burette, you start adding that base. And then once it's done reacting with the acid, then it can react with the indicator, and you get a color change. And you want that color change to happen in the steep part of the pH curve. And today we're going to be calculating how that pH curve comes about using equilibria. So let's review a little bit. This is that polyprotic titration stoichiometry problem that we had in the last lecture on titrations, where we titrated sulfuric acid. It's a polyprotic acid, so it's got multiple protons in the acid group. It has 2, and so once we titrate both of those protons off, then we're at endpoint, and then we can calculate the concentration of that acid if that's the thing that's unknown. And so let's go ahead and compute the various equilibrium concentrations in this particular calculation. So in this titration, we mixed 40.15 mils of this base, 0.1 molar base, and we mixed it with 60 mils of 0.03 molar sulfuric acid. And so we're going to walk through this reaction using the mass action ICE table. So notice the very first step in this, if we're going to do this in the table, is that we have a dilution. You notice how we're adding the base. We're putting in 40 mils of base and added that to 60 mils. So the total volume is around 100 mils. So it's really 100.45 mils. So we've changed the concentrations a little bit. So in our ICE table, we're going to, that first step, we're going to do the dilution step. We're going to take the amount of acid and the amount of base that we added, and we're going to calculate the new concentration of the sulfuric acid. And so after you do that calculation, I'm keeping a guard digit. I'm keeping a 5th decimal place there just to help us with rounding. So we end up with the concentration of the acid at 0.020248. Now in our titration, we stopped it when we had the indicator change, and so the amount of base should equal the amount of acid with the appropriate coefficient, the appropriate mole ratio. And so let's calculate the dilution of the base. We have 40 mils of the 0.1 molar base divided by 100 mils. So this is the concentration of the base. And you see it's around twice the amount of the acid. So that's kind of nice to see. The earlier concentrations, you couldn't really tell it was a 2-to-1. It looked like a 3-to-1. But when you take into account the dilution and the different volumes, then you see these concentrations, when we put them together, are really 2-to-1. And that's what we would expect at endpoint. And then we'll just do this like a regular equilibrium problem. That sulfate, we're going to start with 0 molar. And then we'll do the chemical reaction, the change row. So we lose a mole of sulfuric acid per liter. We lose 2 moles of sodium hydroxide per liter. And then we get some sulfate on the other side. Okay, so since we're going to endpoint, we're going to run out of both of these at the same time. That's the whole point of a titration, is to have both of these run out at the same time. So both of these will go to 0. It doesn't exactly work out because the titration's never exactly perfect, okay? But it's close. You see this is if X is 0.020245, that's about half of this. It's close to 0.020248. But, you know, in the titration, both of these are going to 0. And so we'll go with that. And then our sulfate that shows up is that 0.020245 molar. So this is, I would say this is at equilibrium, but we know that nature really never likes these zeros. And so we've kind of taken this reaction all the way to the products, and then we can let it creep back a little bit to see what the concentration of sulfuric acid would be in the hydroxide. And so let's go ahead and put this in to our equilibrium calculation. Also look at this reaction up here. This is not the typical acid reaction. Typical acid reaction would be the sulfuric acid reacting with water to make the hydronium ion and so on. So let's put that together, and we're going to run this reaction backwards. So let's go back and see. We have sulfate here, and if we run this, if we add this sulfate to water, it's going to pull a proton off the water and make hydroxide and the hydrogen sulfate. So this is the base reaction, that sulfate reacting with water, making HSO4 minus and OH minus. And so now let's see what those concentrations would be. We start out with that amount of sulfate. We have 0 moles of this hydrogen sulfate ion and 0 moles of hydroxide. And then we lose our reactant, we gain our products. And we're going to take this first one, we're going to assume this is a weak base, and so it's going to just move it a little bit. X is going to be small, and so we're going to have that assumption, 0.02 and X and X. So how do we get our pKb? We have the pKa for this acid. This is the conjugate acid here, and that's 1.9. We can look that up in a table. We find that the pKa is 1.9. And so how do we get to the pKb? Remember that the 14 is equal to pKa plus pKb. So that's one of those equations that you have to have stuck in your memory. If you're given a pKa, you ought to be able to get the pKb by subtracting from 14. So here's our pKb value. This is the equilibrium constant for this reaction here. So Kb is 10 to the minus 12.5, or 12.1, sorry, 10 to the minus 12.1. So that's the numerical value of Kb. What's the expression? The equilibrium constant expression is products over reactants, okay? So it's that HSO4 minus times the hydroxide ion concentration over the sulfate ion. And so that's equal to X squared over 0.020245. So if we solve for X, we're solving for the hydroxide ion concentration. So that's the square root of this concentration times Kb. We get 1.26 times 10 to the minus 7. So yes, X is really small. We assumed that it was small, and now we can confirm that it was small. We had 0.02, that's essentially 2 times 10 to the minus 2, and this is 1 times 10 to the minus 7. So that's the concentrations of the hydrogen sulfate ion and the concentration of the hydroxide ion. So those are the equilibrium concentrations. So we've checked this box up here in our problem. We've got that one. What about the pH? Well, this is the hydroxide ion concentration. So what do I do next? Take the minus log, and that will give me what? The pOH, yeah. So we solve for the pOH. Take the minus log of that number. I kept an extra few digits just to keep from rounding errors. So 6.898 is the pOH. Subtract that from 14 to get the pH. So here's our our second thing that we wanted to know. So notice we hit the endpoint, and we have canceled all the acid with the base, and we're pretty close to a neutral, well, not neutral, but pH neutral, around 7, which would be pH 7 would be pure water. We're slightly higher than that, so it's slightly basic. Okay. So that's the polyprotic titration equilibrium. And this is at endpoint. So next we're going to do one that's not at endpoint. And so everybody stretch. This is a long calculation. It's actually 4 ice tables, or 4 tables, yeah, all in one. And so let's look at that problem. First of all, we've done this one. We did the sulfuric acid and the hydrogen sulfuric acid. The sulfuric acid, the first proton is strong. The second one is pretty acidic at 1.9 pKa. Next, we're going to do phosphoric acid. So this is the most complicated example. I don't know of an acid that's got 4 protons that can be removed. Maybe there are some, but phosphoric acid is a classic 3-proton acid. So we're going to do the hardest example today. So if you can understand today, then you can understand any of the difficult problems. Okay. Go ahead and keep up with me and write down all of the numbers so that you stay engaged. But these problems are so long, there's really no hope of me putting this on the test. But stay with me so you can understand it. Because again, this is the hardest one. This is max day. You're lifting the heaviest weight you can lift at this part of the course. So stay with me today. You'll be confident then that you understand how to use these mass action tables and ice tables. So let's do the phosphoric acid problem. And here's the titration curve for phosphoric acid. And here's all of the reactions that are going on in this particular case. So what do you notice? You notice that the protons are coming off one at a time. So as you add base, which is the horizontal axis, the pH is stable for a while, and this is that buffering region where we're converting phosphoric acid into the dihydrogen phosphate ion with base. And we don't see a lot of change in pH as we're adding base until we start to run out of the 3-proton version of phosphoric acid. Once we run out of that version, we get a huge jump, and now we're working on the pKa for this reaction. So the pKa, the 7.2, is, well, I want it right. Okay, there we go. The 7.2 is related to this acid right here. The 2.1 is a property of this acid. So you see, when we run out of that 3-proton version, we don't have an acid in the solution that's going to hold it at 2.1. So it jumps up to the next one, and the pKa for the H2PO4 is 7.2. So we're going to be around that pH for a while until we run out of the 2-proton version of phosphoric acid. Then we get a huge jump in pH, and this 12.4 pKa is related to this one. And it will hold the pH around 12.4 until we run out of it. And then up here, we're just looking at the pH of adding hydroxide to water. Okay. All right. So if we titrated to the third endpoint, we could use this overall equation here, this H3PO4 plus 3 hydroxide and so on. But if we stop short of that endpoint or go past that endpoint, we need to do the equilibria reactions for each one of these. And so this requires that we go through each of these reactions one at a time until we run out of hydroxide. So then we know where we are at pH, what pH we're at. And so this is a maximum of 3 limiting reactant problems where we run everything to 0 and then take that last row and move it to the next initial row and do the next reaction. So we're going to do all 3 of these reactions, walking through the limiting reactant problem, and then we'll end up with a final equilibrium problem based on this reaction up here. So this is the equilibrium reaction with this single proton acid and water making the phosphate ion. So what are the equilibrium concentrations in pH? Whenever we have 30 mils of a 0.1 molar sodium hydroxide solution mixed with 11 mils of a 0.1 molar phosphoric acid solution. So it's not quite 3 to 1, right? If it was 30 to 10, it'd be 3 to 1. We've got a little bit more acid, so we're not quite at endpoint. Okay. And so that first step, again, we have volumes and concentrations of our acids and our base. And so we're going to do the dilution step first. We mix 30 plus 11, so we have 41 mils. So the new concentration of our acid is 0.02683. We're doing titration, so we're going to keep all those digits. The hydroxide concentration is 30 mils times the 0.1 divided by 41 mils. And so it's 0.0717. And then we're going to start with 0 molar solution of H2PO4. All right, notice that they're coming off 1 proton at a time, so all of our X's are just either minus X or plus X. There's no 2 X's or 3 X's or anything like that. So we have 2 minus X's on the reactants and a plus X on the product. We don't worry about water, it's the solvent, it's a liquid, doesn't play a role in the equilibrium constant calculation. So let's take these, one of these is gonna run out, right? And if you look at that, you got 0.02 and 0.07. The 0.02 is going to run out. We're going to run out of that 3 proton version of phosphoric acid. And so that means that X is 0.02683. And so we're going to subtract that from the 0.07. And so now we still have hydroxide left over. We have 0.04634 moles of sodium hydroxide per liter solution. And then X is 0.026, and so that's going to show up as the H2PO4. So let me pause here just so you know what's going on. It's a limiting reactant problem. We're not doing equilibrium yet. So we've run out of one of the reactants, and we have our reactant that's remaining, the hydroxide ion, and we have the product, which is also an acid. So what's this going to do? The hydroxide is going to react with the product and steal protons from the product. That's a whole new calculation. So that's going to go on the next page as our initial concentrations. So we'll start a new reaction with this one. We'll take this one and add hydroxide. And we'll make the H1 version, H1PO4 plus water. Right? So see how this, we've got excess hydroxide. It's going to keep reacting with the acid and pull the second proton off. So that's our next reaction. While we're here, though, I want to just quickly look at this 0 molar. I mean, nature hates zeros. And so just as a side note, let's do a real quick equilibrium calculation. And there's a quick way to do this. Look at this reaction. This is acting like a base if we run it backwards. So this is H2PO4 plus water makes hydroxide and H3PO4. So this is a KB reaction in reverse. So that's the reverse of this reaction here. And so how would we write the equilibrium constant expression for a reverse reaction? That was one of the ones about 2 weeks ago or a week and a half ago. I had a reaction on the homework, and then I had that reaction flipped. What did I do to K? 1 over, because the products are now reactants and reactants are now products. So if you flip the reaction, it's 1 over K. Now I want to see nods on that. Everybody got that? You flip the reaction, you flip products and reactants, the K, it becomes 1 over K. So we can do that, can't we? All right, this reaction as it's written, okay, the product is H2PO4, the reactants are H3PO4 and hydroxide, and that's 1 over KB. Okay, and so KB is equal to KW over KA. So if I flip that, it's KA over KW. So I have all of the numbers here, and I can solve for this guy right here. This is my X. Just a real quick equilibrium calculation to get rid of that 0. So I have X down here, and I have all of the other numbers. If you're not following me, go watch the video. This is just a side trip to get rid of that 0 just for fun. Okay, so X is 7.3 times 10 to the minus 13. That's pretty close to 0. So we got a lot of base. We've ripped all of the protons off of the first, all of the first protons off. There's a small chance, like a 1 in 10 to the 13 chance, that there'll be an H3PO4 running around with 3 protons. But as soon as it finds one of these base molecules, it's going to get stripped off. Okay, so that's the side sort of equilibrium calculation. Let's take these two here, right here, and move to the next ice table for this reaction that I've drawn up here. So we've got that new reaction, H2PO4, reacting with the residual base, making HPO4 in water. So these two new concentrations are from the previous page, the E row. Okay, so again, the minus X, and plus X, because it's just one proton at a time. And so we have more base than this amount of acid, so we're going to take the acid all the way to 0, and we're going to subtract that amount from 0.04, and we have the amount of base, 0.01951. And then X is 0.026, and so it's going to come down. We have now 0.026 of this acid. We have excess base, and so now this one's going to react with base to produce the PO4 3 minus plus water in our next calculation. And we'll just take these bottom two concentrations, the HPO4 concentration and the base, and we'll do another reaction for that. Okay, but that's the next calculation. So we've done 2 of our limiting reactant problems. Let's go ahead and get rid of this 0, too, just to see what it is. Like I said, just for grins. This is the reverse of that KB equation. So it's a base reaction in reverse. Well, this is using the Ka instead of the Ka2 instead of Ka1. So the Ka for this reaction, for this particular species, up here is 7.2. So pKa equals 7.2 for this particular species. We saw that in the previous table. We saw it on that chart. So we know all of these values except for X. We can solve for X. And now this is 2.2 times 10 to the minus 7. So it's a lot more likely to find a few of these. It's almost impossible to find an H3PO4 because we have so much base. But it's a 1 in 10 to the 7 chance poking around in that solution and finding an H2PO4 minus. Okay. So that's the equilibrium piece, getting rid of that 0. So this number here obviously would go right here. You've heard the phrase, nature abhors a vacuum. Any of these 0 molar solutions, that's a vacuum. I mean, it's going to be filled with something, even if it's a small number. It's probably not 0. Okay, so let's now take these 2 concentrations here for the hydroxide and the acid and run them in this next reaction. This is our third and final limiting reactant problem. So those concentrations go in here for the base. We have 0 molar phosphate. The change row is, you should be familiar with that by now. Minus X on the reactants, plus X on the products. And we look at this and we have less base. So we're going to run out of base, finally. You get that down to 0. Subtract that from the 0.02683. And we end up with a really small amount of acid left over, 0.007320 molar. And then we add in the 1951 for the phosphate. So do you see how these are limiting reactant problems? We did 3 of those as we're going. We're always running out of something, and we get to the end. And now we have an equilibrium calculation because we have a 0 here. And so we'll do that equilibrium calculation next. Okay. So this is the reverse of that base reaction. Now we're using the third Ka. So pKa for this guy here was equal to 12.4. And so now we know all of these. We know that this Ka value here, the water, we have the concentration of the product, we have the concentration of the reactant, and we're solving for the hydroxide ion concentration. So it's 0.06695. So that's a pretty big number. So that would go here. Okay. And so that's our equilibrium step. We could do this in a more traditional way if we took this this PO4 here and this other HPO4 2 minus, and we added those in with water. So this is the more traditional way to do that equilibrium calculation. So these concentrations came from that last row, and this is your traditional ice table equilibrium calculation. So if you didn't like that whole reverse KB thing, this is a more traditional equilibrium calculation. You just take those last concentrations, the one for this guy here, the one for this guy here, okay, and you could write your regular ice table calculation. So the acid reacting with water, forming the conjugate base, plus hydronium ion concentration, and you could run this as a regular ice table calculation. I've just blocked out that whole water thing just so we don't have a blank column there. So again, minus X for the reactant, plus X for both of the products. We end up with X for the hydronium ion concentration, and these are going to be some small x's, we'll assume, and then we can put these into the Ka calculation. So we have the acid, the equilibrium constant expression here. Again, from the Ka, the pKa comes down here. So it's the anti-log of that. We solve for X, and we end up with this really small number, this 1.5 times 10 to the minus 13 hydronium ion concentration. So we could take the pH of that, the minus log. I don't know why I have that. I must have changed numbers. Let me change this out. 1.49. One of those is right. I don't know which. You might have to check me on that. And that's equal to 12.8. So it's a pretty basic pH because we've had a lot of base. It's reacted with the acid, but it's still way up there in the basic range of 12.8. We had to get, we're up there in the equilibrium region with this acid, and this acid's proton does not come off until the base concentration is, up in the pH of 12.8 range or 12.4. And so then the POH is 14 minus that, or 1.2. And so if we calculated the base concentration that's available at that pH, it would be that 0.0669, which we calculated on the previous page. So that is the titration equilibrium problem for a triprotic acid. Really long, fairly tedious, 3 separate limiting reactant problems. As you run out of acid, you're going to keep titrating more and more of the products, which are also acids, and then you get up with an equilibrium calculation. Now we could do this same thing, this last equilibrium calculation using the Henderson-Hasselbalch equation. If we recognize that this is the base, so this would be the concentration of the base right here, and this is the concentration of the acid, then here's that Henderson-Hasselbalch equation, which is, again, just a rearrangement of that equilibrium constant expression. And so we can put in all the numbers, 12.4 plus this small adjustment that's based on the log of that ratio of base to acid. And so that's going to give you the 12.8 that we calculated before. But notice if you, I mean, you don't really even need the table. If you just recognize that this acid is right there and this base is right here, then as soon as you know what those two species are, their concentrations, you can go straight to the Henderson-Hasselbalch equation and calculate it. You just have to know the correct pKa for the acid that you're using.
Does this only work for monoprotic acids?
Well, see, this is a polyprotic acid, but they all happen one proton at a time. And so we're at the third proton. So we need to use the pKa3 here. So you need to know where you are in terms of that titration or that equilibrium system. Like if you mix phosphoric acid with a close to 3-to-1 ratio with base, you've already titrated the first one off, you already titrated the second one off. You have so much base, you know you're at the third proton.
So let's say if we start at like H3PO4, do we have to do the Hasselbalch equation 3 times?
No, it won't work because if you try to use it for the first proton, you're essentially taking the log. There's so little of that first proton species, the acid concentration, that you're essentially, the correction term is like the log of infinity. Okay, you've got to find the correct range of equilibrium that you're in. So you still have to do some sort of limiting reactant problem to kind of find out if it's a polyprotic acid. You have to find out where you are in terms of which proton equilibrium you're at. You're at the first proton equilibrium, which would use Ka1, or pKa2 for the middle range. So if we mixed it, if we had, say, 1.5 times a ratio of base to acid, we would have already, the one part, so 1.5 times the base to acid, the one would titrate all of the first protons off. And then the half would be titrating the second protons off. So I'd be working on the second proton equilibrium. So you could just kind of look at that and say, okay, in the mole ratios, I've got 1.5 times the amount of base that I have acid. So that would tell me I'm in the second proton. Here we're close to 3 times, and so we know we're in that third proton equilibrium. And so then the pOH is 1.2, the pH is 12.8. Okay, same kind of results that we got for the previous one. So here's the titration curve, and I just pasted in all of the ice tables that we used just to help you kind of see what we did. We noticed how we took this first one, the H3PO4, went down to 0. We took these two here and moved them to the next table. Then we took this acid down to 0. Okay, and then we took these two to the next table. So this one went over here. This one went over here. And then we had to look to see which one's going to go to 0 here. This is the smaller number, so the hydroxide went to 0. Again, it's a limiting reactant problem, so that's always a temporary step. It went to 0 temporarily, and then we do the equilibrium to see how it shifts back. Okay, so we took it to 0, and then we had these concentrations, and we took this one, and we put it up here, and we took this one, and we put it right here. And then we could use the Henderson-Hasselbalch equation now that we know which proton we're working with. We had the pKa for this guy right there was equal to 12.4. And so we could go right into the HH equation, put in our C base and acid, and we could get the pH. And then we could also calculate the hydronium ion concentration, and that was something like 10 to the minus 13. So that's as complicated a titration problem as you'll ever see. We're not at endpoint, and we've got 3 different protons coming off. And hopefully this shows you what's going on at each region in this curve. Now, just for your benefit or whatever, I did the same problem with a different method. And so I'm leaving this one for you just to see if you can figure it out. I went ahead and did the full, titration, took the base down to 0, and ended up with these 2 concentrations of the phosphate and the H3PO4. But the problem is we can't go straight to the Henderson-Hasselbalch equation for this result. And I want you to chew on that. Why can't we? Why can't we take this product and this reactant? We've got a base and we've got an acid. And I know then C base and C acid, but I can't use the Henderson-Hasselbalch equation for this. Do you know why?
The protons are coming off one at a time.
It's related to that. Whenever we're using the Henderson-Hasselbalch equation, we're talking about equilibrium, the base has to be the conjugate base for that acid. And this is not the case here. This acid produces H2PO4 minus. So if we use the Ka for this acid, which Ka was equal to, was it 2.1? Someone look back in the notes and see what the Ka for that was. Yes? Okay, so this Ka of 2.1, or pKa I should say, pKa is for this acid, but only when it's in equilibrium with this base, okay? So we can't use Ka1, we can't use Ka2 because we've blown past that. What we really need to know is what is Ka3, right? We've got this concentration here. We've got to figure out what the concentration is for the HPO4 2 minus. So I'm going to just make up a reaction because this guy is a pretty strong base, this PO4 3 minus, and this is a decent acid. And so I'm just going to react this product with the remaining reactants. And so look at this reaction here. I've got some H3PO4, and it needs to produce H1PO4. And I've got PO4s here. So I've got 3 protons, so I know I need to create 3 of these, which means I need 2 of these for this reaction to balance. And so I've just balanced this reaction, and I've done this as a limiting reactant problem. So this is going to go away to 0. This is going to go away to 0.01951, and this is going to increase to the 0.007320. So all the numbers should be, you might recognize those from the earlier problem. And so now I have my C acid, my C base. I've got this single proton that's going to be the pKa3, and now I can use the Henderson-Hasselbalch equation. So here's the H3PO4, the PO4. I've got C acid, C base, and everything's fine. But this step, I don't know, that's a pretty big stretch perhaps for you guys, but I left it in here as a second method to do the same problem. I did it in 3 steps instead of 4 steps, or maybe 5, depending on how you count. It was a lot faster, but this piece right here in the middle just involved me thinking about the reactivity, okay? And so I leave that in there for your own benefit. If you really want to try to chew on how these things are done, try to understand that alternate method for doing this problem. All of the less stuff in this lecture today was really what we would call enrichment. It's pushing you further than you're going to be tested, but it's something that you'll need in future classes and so on. So don't just discount it. Certainly, I don't want to hear a flushing sound when you leave the classroom. That's probably the #1 problem in education, specifically in college, is that you don't retain stuff very well from lecture to lecture, but really the big problem is going from course to course. And so when you leave every course, do your best not to just throw that material away, okay? Save your notes, be able to go back and review things. That's part of why we as faculty, I'll go on the record, I don't like the Bearcat Bundle. I don't like renting books. I think you should build a library, and you should have that permanently, you know, and so think about that. Think about building your library so that you don't have to remember everything. And when you're given an actual problem, you actually have time to solve it. You can go to your library and pull your freshman text off and flip to the equilibrium section and redo this learning. You know, you're not going to remember everything, but try to remember as much as possible, because that's the one thing that hampers you in the future classes. All right, y'all have a great weekend.